Data duplication kills financial reconciliation and inventory accuracy. At least once delivery is the default, but it mandates complex downstream deduplication logic. Exactly-Once Semantics eliminates this operational burden directly at the source. The first step is enabling producer idempotence. Set the configuration parameter enable.idempotence to true. This guarantees that a single producer instance writing to a single partition will not introduce duplicates, even upon network retries. Kafka achieves this by assigning a unique producer identifier, the PID, and a monotonically increasing sequence number to every batch of records sent. The broker tracks the highest sequence number successfully written for each PID and partition combination. If a producer retries a batch with a sequence number lower than or equal to the last committed number, the broker silently discards the duplicate request, ensuring the message is written exactly once. Idempotence only solves duplication within a single producer session writing to one partition. Achieving atomicity across multiple partitions or topics requires the full transactional producer. Define a unique transactional.id for the producer configuration. This identifier allows the transaction coordinator, a dedicated component within the Kafka broker, to manage the state of the producer's ongoing transactions. Before sending any data, the producer must call init transactions. This registers the producer with the coordinator and retrieves the producer's current epoch. The epoch is a crucial mechanism for fencing. If a producer attempts to initialize a transaction with an older epoch, the coordinator rejects the request, effectively preventing zombie producers from corrupting the transaction log with stale writes. This fencing mechanism is fundamental to maintaining data consistency.
A transaction begins with the producer calling begin transaction. All subsequent send calls are buffered by the producer client and marked as part of the current transaction. These records are not immediately visible to standard consumers. The transaction scope can span multiple topics and partitions. If the producer fails before committing, the entire set of buffered writes is discarded. The producer must handle exceptions during the send phase, deciding whether to abort or retry the transaction. The core benefit is atomicity. Either all messages within the transaction are written and visible, or none are. This simplifies application logic significantly by removing the need for distributed two-phase commit protocols outside of Kafka. Many integration patterns involve consuming messages, processing them, and then producing new results. To ensure Exactly-Once Semantics in this read, process, write scenario, the consumer offsets must be committed atomically with the produced messages. After processing the consumed records, the producer calls sendOffsetsToTransaction. This method takes the consumer group identifier and the specific offsets to be committed. The offsets are not immediately written to the offsets topic. Instead, they are bundled with the transaction data. This ensures that if the transaction fails, the offsets are not committed, and the consumer group will reprocess the original input messages upon restart, preventing data loss or duplication during failure recovery. Once all messages and offsets are prepared, the producer calls commit transaction. This triggers the transaction coordinator to finalize the transaction. The coordinator writes a special control message, known as a transaction marker, to the logs of all partitions involved in the transaction, including the offsets topic. This marker indicates that the transaction has successfully completed. Only after this marker is written and replicated does the data become visible to consumers configured for committed reads. If the producer encounters an error during the commit phase, it must call abort transaction. The abort process also involves writing a transaction marker, signaling that all records associated with that transactional identifier and epoch should be ignored by consumers.
The visibility of transactional data is controlled by the consumer's isolation.level configuration. The default setting is read uncommitted. Under this setting, consumers read all messages immediately, including those belonging to open or aborted transactions. This configuration violates Exactly-Once Semantics and should only be used when latency is paramount and downstream deduplication is already implemented. To enforce EOS, set isolation.level to read committed. Consumers configured this way will only read messages that are part of a successfully committed transaction. They skip any records belonging to open transactions and discard records marked by an aborted transaction marker. This setting is mandatory for reliable integration pipelines. The transactional producer relies on the transaction.timeout.ms setting. This defines the maximum time the transaction coordinator will wait for a producer to commit or abort an open transaction. The default is typically 1 minute. If the producer fails or crashes without explicitly closing the transaction, the coordinator will eventually time out the transaction and automatically abort it. This prevents indefinitely locked data.
System analysts must ensure that the application's processing time, including external service calls, remains well within this timeout window. If processing exceeds the timeout, the coordinator will fence the producer and abort the transaction, leading to reprocessing upon restart. Implementing Exactly-Once Semantics introduces overhead compared to simple at-least-once delivery. The primary performance cost stems from the increased network round trips required for transaction initialization, committing offsets, and writing transaction markers. Furthermore, the broker must maintain state for every active transactional identifier, increasing memory usage on the coordinator nodes. Throughput is generally reduced and latency increases due to the requirement for synchronous writes of the transaction markers. Benchmarking is essential. Measure the baseline throughput and latency before enabling transactions. A typical throughput reduction of 10 to 20% is common, depending on the transaction size and frequency. Optimize transaction batching to amortize the commit overhead.
Monitoring transactional health requires tracking specific metrics. Watch the producer's transaction in-flight count to detect producers that are failing to commit or abort. High counts indicate potential resource leaks or application deadlocks. On the broker side, monitor the transaction coordinator's response times and the number of aborted transactions. Frequent aborts suggest application instability or inadequate transaction timeout settings. Ensure that the transactional.id is managed carefully. Reusing IDs too frequently can lead to unnecessary fencing overhead. For high availability, ensure the transaction coordinator topic, internal offsets, is adequately replicated across multiple brokers to prevent single points of failure in transaction state management.